Hi, I'm Shushin. I'm a PhD student from University of Eastern Finland and in Riga, Nancy. In this work, I'm going to present a comparative reassessment of feature extractors for deep speaker embedding models. So as you can see, a typical speaker verification system is usually divided into three major modules: feature extractor, speaker embedding extractor, or speaker classifier sometimes, and a backend score. Feature extractor use waveform as input and they create acoustic features. Speaker embedding extractor uses features to train itself and create embedding from inference data. And the backend score use embeddings and adaptation data to train a typically PLDA-like model and produce likelihood scores on specific trials. Many people these days, they celebrate the emergence of deep neural network-based speaker embedding extractors, replacing conventional approaches such as GMM, SVM, and X-vectors, etc. Good examples of those neural stuff are D vectors and X vectors as shown here. Lots of amazing works on improving it in many ways are there, such as extended or factorized TDNN, generations of TDNN, self-attention pooling, self-statistic pooling, multitask learning, angular softback as loss function, and multiple data augmentation technique, etc. But most of those models are using typically standard, also called male frequency capture coefficient, or their intermediates, such as raw spectrum or male phase bands or log male as shown here. Meanwhile, we know MFCCs are not taking care about many other attributes, such as phase spectrum, temporal operations, etc. And there are some works that does, for example, features using group data function, temporal masking, or even neural net approaches. Let's give us a question. Why not just simply replace MFCC with some other excited handcraft feature from earlier work on I-vector systems, SVM, as we mentioned, or other speech tasks such as speech recognition and spoofing? So we kind of focus on this module here. So in this work, we give a benchmark on 14 handcrafted different acoustic features, including baseline, to see if our hypothesis is true and there are alternatives from MFCCs in the history book. We review early literatures on speaker verification, as well as other speech processing tasks, such as scientific spoofing, playback tag detection, and speech recognition, etc. We divide those features into three categories with an additional trial on pitch factor. I will quickly go through and evaluate them on a X vector plus PLD backend setting. We hope this will shed some light and give some suggestion to the community on alternatives for deep learning powered speaker verification systems. So the first category includes features using magnitude or power spectrum. You can see MFCC belong to this category since it uses power spectrum, as we know. We also have constant Q capture coefficient, or we call CQCC, where instead of DFT-based spectrum as shown with MFCCs, inventor of CQCC use CQT-based spectrum to give variable resolution across time frequency representation and potentially more fruitful spectral information. We also have linear prediction features like LPCC and perceptual LPCCs, where we use all pole representation of signal and recursively derive features from linear prediction coefficients. PLPCCs are actually LPCCs plus a series of perceptual steps to follow. We also have spectral subband centroid-based spectral features here, where we compute weighted average of normalized subband magnitude energies. If we compute from frequency energies, it will be spectral centroid frequency feature that we call SCFCs. We can then apply log plus discrete cosine transform called DCT to get magnitude domain features. It will be SCMCs, ambient magnitude. Finally, we have multi-step MFCCs, where instead of one shot window plus DFT spectrum estimation, we have multiple windows, or we so-called tapers here, producing subspectral and get a weighted sum of them to have the spectrum in place. Both taper function and weights are static and computed using specific static math techniques. For detailed information, please refer to the work relevant shown in the reference list. Moving on to the second category, where we started to incorporate or just use phase spectral information into the feature estimation. Speaking of this category, we can get a relevant concept of group delay function, which is a non-parametric technique applied to signal directly. We know usually in MFCCs, phase spectrum is ignored because we can't have a proper continuous distribution of phase, which is the principal one. Group delay function can sort of solve this problem, having continuous estimating while sharing properties similar to phase spectrum. Here we have two feature extractors based on this. First, modified group delay function, what we call MGDFs, applies it to DFT transform of the frame signal as shown here. turn it into a parametric technique by gamma and then alpha, as shown here. R and I here means real and imaginary parts of the complex representation from discrete Fourier transform. On the other hand, we can combine group delay function with the output representation of a spectrum having fewer number of parameters. We have other two features that are not dependent on group delay function and thus kind of simpler from our perspective. Cosine phase function or cos phase, where we apply cosine function on the unwrapped phase spectrum, and constant Q magnitude phase octave coefficient, or we call CMPOX, where we combine magnitude and phase in the way showing this formula, and perform octave segmentation, followed by a DCT to get the coefficients. Then we come to the third category where we begin to have cross-frame, or some people call temporal long-term operations into the processing pipeline. Here we have two features involved which deal with temporal signal envelope here in a different way. Left-hand side, main Hilbert envelope coefficient MHEX performs a linear smoothing on the filter banks with the Hilbert transform, as we can see here. On the other hand, PNCC is a bit complicated on this, and from my perspective, by a series of masking and filtering operations. It is more targeted to reducing noise effect. We won't spend much time on explaining this, and welcome people interested to check original work, which is shown at the end of this video reference list. Of course, we won't ignore the bonus fundamental frequency feature where we call the pitch extractor and attach it to static MFCCs. The three-dimensional vector for each frame is extended from the so-called normalized cross-correlation function, NCCF, and consists of pitch, NCCF value, and delta value of a log of pitch. Again, for the detailed information, please refer to the original work. Okay, speaking of experiments, we use VoxLab1 and the standard 2018 X vector with statistic pooling. We also perform score level fusion on multiple single system, one using only magnitude-based spectral features and the other one using one feature from each category. For evaluation, we follow standard protocol of VoxLab1 as speakers in a while, which can be checked later. Speak on matrix, we use equal error rate and minimum detection cost function, and Bosaris produced detection error to occur. And here's our results on VoxLab. We just show it selectively here, so to keep people focused, and for more detailed one, please check our paper. So first of all, best in-domain single system performance come from SCMC in terms of ER, aside from the fact that MFCCs actually outperform the most features under this matrix. Speaking of minimal detection cost function results, MFCC with pitch seems to work well, as well as multi-taper, which further confirm their efficiency. Those findings prove that those kind of attributes, such as spectral central information and pitch factor, can potentially be extended and potentially be useful for speaker verification systems. Results on speakers in a while are interesting as well, as we can see improvement for more features. I didn't show them all here due to space, and encourage people to check more on paper for this part as well. Anyway, best performance comes from power normalized capture coefficient in terms of both categories. They also note that it actually outperformed both fusion systems as well, which may indicate the effectiveness of such nonlinear time-varying operations on speaker verification, not only for speech recognition, like what it was proven in the original PNCC work. In terms of dead curves, we will plot some system here for the sake of clarity. We can see performance and improvement mostly matches statistical results from both evaluations. Although at right bottom of the speakers in a wild plot, the right-hand side, we can see both spectral central features are heading out, so probably those features are a bit of favor in two cases where we are less strict on false alarms. Surely there are also some other findings, but we keep it short here. Please check the original paper if you're interested. Okay, so what's next from here? It is a benchmarking work, but something needs to be further from here. First of all, as straightforward as it is, people may want to switch from MFCC framework and embrace different feature extractor, for example, spectral central features and power normalized capture coefficient, especially if people would like to chase for robustness. At least that's what's been reflected here. Creating fusion system can be useful, but it requires more workload and resources, as we know, so single system might be a better starting point. Second, along implementation and analysis, we found multiple useful speech attributes that is relevant to features, such as phase information and spectral centuries. Again, they might be interesting and might be useful for feature and also model-based encoding and adaptation, for example. Finally, temporal, or we say long-term operations, is useful for sure on robustness, as we've shown in the last couple of slides, and can be considered and extended in a similar way to not only feature mode but also speaking about extraction motion as one of the extensions. So as a benchmarking work, we believe it will open a bunch of new other directions as well, and fresh stuff from old features to the community. Please feel free to discover more using this paper as a starting point. And here's a selective list of references. Some of them are addressed during the presentation. And that's it for this video. If you have any questions, feel free to send email to me via the email address here, or just ask and criticize during the session. And yeah, that's it. Thanks for listening.